All right, very good. So for the next little while, welcome to everyone that joined us. This event is organized by the Faculty of Mathematics. We hope that this is a way to get some of you here later in life. Maybe not. We'll see. You actually maybe will end up at the far end of the universe. I don't know. Like Trevor did. Trevor, the Time Traveler, is a book written by our guest tonight, Professor Hubert Bray from Duke University. So I don't want to spend any more time introducing him because you'll spend enough time with him now that you'll get to know him. So there you go.
So thank you to Benoit and the University of Waterloo for this invitation to speak here. I'm having a great visit. It's a great university and enjoy this y'all's home here very much. Thank you for your hospitality. So I am a professor of math and physics at Duke University, but I'm also a father of 5. And I've always been, I always wanted to know how the universe worked. That's been a passion of mine since I was a kid. And you know, I'm living my childhood dream right now to get to do research in math and physics. And so the first thing I'd like to say to all the kids and young people in the audience is that whatever it is your dream is, work hard, try hard, be passionate, and you can achieve it. Don't ever underestimate yourself. Look around and ask yourself, okay, I want to do this. And look around, someone's going to do that. And the question is, why can't it be you? And the answer is, there's no reason why it can't be you. But it takes a lot of hard work, though, obviously. And you've got to do really well in school and learn as much math and physics and other things as you can. Now, I always enjoyed reading and writing. That was one of my, I always had a good time. I was always better at math, though. Math was always my best subject. But I always liked writing and reading and books. And when I never felt the need to write a book my entire life, although I am a writer. You know, as a mathematician, what do? I sit around and write papers. Right? I'm constantly coming with ideas, and then I communicate those ideas in the form of papers. And so I do write for a living. But it wasn't until very recently, a little over a year ago, that all of a sudden I felt like, wait a second, it was my kids inspired me to write a book. And they were really interested in Star Wars. And there's this show called Doctor Who. Have you all ever heard of Doctor Who? He has a time machine. It's a British show. And my son got really interested in that. And so I just got like, oh, okay, could I come up with a story that's kind of like Star Wars, but not nearly so violent, right? And, but that would have lots of good life lessons in it, and also teach math and physics, and just be a lot of fun, right? And so this is what inspired me. This kind of happened. So maybe someday, might not be a writer yourselves, but someday you might just be inspired to write a book, and you can do that as well. So Trevor the Time Traveler really has a lot of true science in it. So, for example, the backdrop of Trevor the Time Traveler is really described by the cover here. So there is, these are actually photos of real galaxies, by the way. It's really quite remarkable photos. This photo here is a picture of the next closest galaxy to us. So we're in the Milky Way galaxy. This is a picture of the Andromeda galaxy. It's the next, it's the next closest big galaxy closest to us. And that photo was taken by the Hubble Space Telescope, which is a telescope that costs billions of dollars to make and is in orbit in outer space. We should just sit and appreciate that for a second. Is that you've seen telescopes that you can buy, and you can get a big telescope and put it in your backyard, and then you got the observatories, right? So, someone built a telescope, put it on a rocket, launched it into outer space. It turns out it had something wrong with it, so they sent the space shuttle up to fix it. They did the repair, and then they took that photograph. All right, there was a tremendous amount of effort to give us that photograph. We are living in an amazing time. We are living in a time that's rich with data about the universe. And we're learning new things about the universe as we speak. So that photograph really blows me away. This photograph blows me away too. This is a picture of a galaxy that looks something like our Milky Way galaxy. But it's not I wanted a picture of the Milky Way galaxy. But it turns out you can't get a picture of the Milky Way galaxy. Can anyone tell me why? Yes? Yeah, we're in the Milky Way galaxy, right? So the only way to take a picture of the Milky Way, you have to go out of the Milky Way galaxy and look back. But here's the problem. Do you realize that that's like 100,000 light years across that galaxy? The Milky Way galaxy is about 100,000 light years across. What that means, and let's just marvel at how big the Milky Way galaxy is that from one side of the Milky Way galaxy to the other is 100,000 light years. Now you're asking me, what's a light year? Does anyone know what a light year is? Yes?
It's the distance that light can travel in 1 year.
That's right. It's the distance that light can travel in 1 year. Now let's just consider what that means exactly, right? I mean, doesn't light go infinitely fast? Yes?
It just means that light takes like 100,000 years to get from one side to the other.
Exactly right. So to be 100,000 light years across means it takes light 100,000 years to get from one side to the other. Now let's consider how fast light is. Turns out light is not infinitely fast. When you see me, light has hit my face and has bounced off my face and it gets to you very, very quickly. In fact, does anyone know how fast light goes? Is it faster than, how much? All right, so good guess. Yes, do you know how fast it goes?
It can go around the Earth 7 times in 1 second.
7 times in 1 second? That sounds about right. Light from the sun takes about 8 minutes to get to us, and that's 93 million miles. Okay, I'll tell you the exact number. It goes 300,000 kilometers. Now, 300,000 kilometers, that's a long way, right? 300,000 kilometers per hour? No, per second. Light goes 300,000 kilometers per second. So it's amazingly fast. And yet, it's going as fast as that. It still takes light, not a year, 100,000 years to get from one side of the Milky Way galaxy to the other. So these are tremendously large distances. So our home, the Milky Way galaxy, is a tremendously large place. In addition to it being tremendously large, there are also a tremendous number of stars in the Milky Way galaxy, as this picture shows. Y'all think it's more or less than 1,000? Yes?
More.
More, okay, you're right. More or less than 1 million? Someone else? More, that's right. How about more or less than 1 billion? You're right, more than 1 billion. And in fact, Milky Way galaxy has something around 300 billion. These numbers are so big, it's hard for me to keep track. There you go. 300 billion stars. Hey, you cheated. No. So the Milky Way galaxy, so that's what 300 billion looks like, by the way. That's a lot of zeros, isn't it? Okay. The Andromeda galaxy has even more. It has 1 trillion stars. 1 trillion. Like, the only way to understand what 1 trillion is like the national debt of the United States government. I mean, other than that, it has no meaning whatsoever. So, I mean, it's just hard for us to comprehend how big these galaxies are. Now, it gets better or worse, depending on what different issues you may have with this. The galaxies are tremendously big, 100,000 light years across. There's tremendous numbers of stars, hundreds of billions to trillions of stars in each galaxy. But how many galaxies are there in the universe? I mean, those are 2 of them. Are there others? Well, you probably guess others. Maybe more or less than 20. What do you think? Yeah, go ahead. Yes?
There's like an infinite amount of galaxies because the universe is infinitely big.
That's a great answer, actually. The answer given was that there are an infinite number of galaxies because the universe is infinitely big. Well, actually, it turns out we don't know how big the universe is. It might be infinitely big, or it might not be. It's just simply we don't know. And one thing I would like to emphasize is there is a lot of stuff we don't know. And even of the stuff we don't know, there's also a lot of stuff I don't know. All right? So I think there's definitely, people keep on measuring the big shape of the universe, and they're trying to see if it curves up on itself or not. And so let's just take a side step here. But before, how about this? Let me just restrict the question before we go off on that tangent. How many galaxies are in the known universe, the part of the universe we can see? Does anyone want to make a guess? More or less than, let's say, a 20. More or less than 20. Yes?
More.
You still think more, okay. How about more or less than 1 million? That's a lot. Yes?
I would say probably less.
Less than 1 million. Because 1 million is a ridiculously large number, right? You count to 1,000 times to get to 1 million. But it turns out there's more. Okay, how about a billion? Do y'all think there are more or less than a billion galaxies? Yes?
It's
More than a billion, right. And in fact, in the known universe, it's around 100 billion, right, in the known universe. Now, the reason this is worth contemplating, if there are 100 billion galaxies, and each galaxy has over 100 billion stars, how many stars are there? I don't even know how to say what that number is. It's 100 billion times 100 billion times whatever, even more stars in the universe. Okay? The universe, even the known universe that we can see, is mind-bogglingly large. And why that's relevant, actually, for the story of Trevor the Time Traveler, is that with that many stars out there, how many of them have life on them? Now, probably none of them have life actually on the star itself, right? That would be kind of silly. But it turns out, what's the sun? Yes?
a star.
It's a star. That's right. Our sun is just a star. So it so happens that our star, which we call the sun, has 8 planets orbiting it. And some of those planets have moons orbiting it. And there's life on the planet Earth. We're even looking for life in our solar system, right? The question is, did Mars once have life on it? Is a reasonable question. It did, in fact, once have running water on it, apparently. And so that gives the possibility maybe there could have been life a long time ago on Mars. Probably not, but you never know. Also, there's a moon of Jupiter called Europa that has a solid ice surface, but it's water ice. And because of possible geothermal heat on the center of that moon going around Jupiter, it's called Europa, possibly that ice gets melted on the inside. Possibly. There could be liquid oceans on Europa, which is a moon of Jupiter. And life on our planet seems to have begun in the ocean, so it's certainly possible that if you have liquid water oceans on Europa, maybe there's even life there. Right? So that's our solar system. Now the question is, do most other stars, do they have planets going around them? Turns out the answer is yes, it looks like. This is stuff by the way, astronomers only realized this in the last 20 years. I mean, this is very recent work, because the next closest star, by the way, is 4 light years away. It takes like 4 years. The next closest star is so far away, it takes like 4 years to get there. So when you look through a telescope at the next closest star, it's very hard to actually see any of its planets, because you can see the star, but you can't see the planets. But what you can see, though, is you can see that the star is wobbling a little bit. And the fact that the star is wobbling a little bit means that there must be other stuff with gravity tugging on it. And when a planet orbits a star, it causes the star to wobble just a little bit. And based on the wobbling of stars, they come to the conclusion that, in fact, planets are incredibly common, and probably most stars have planets going around them. So this means that of the 100 billion galaxies, each with 100 billion or more stars, that each of those probably has multiple planets. And now the question is, do any of them have life on them? What do you guys think? Yes?
If there's so many of them, it's very unlikely that the answer to that question is no.
Yeah, it does seem unlikely. The answer is no, doesn't it? Yes?
Actually, since one of the closest stars is like 2 stars orbiting each other, so it would be really hard to be planets there. But we did find a planet that's a gas planet like Jupiter that's close to the star, but I don't think there would be life on there.
Yeah, on a gas planet, it would be hard for us to imagine anything, at least not life like us, right? It would have to be something very, very different from what we can imagine. And let's just face it, our imaginations just aren't that good, right? So look, we're asking questions we don't know the answer to. Okay, so let's just come back with a big, fat I don't know. Does there exist life elsewhere in the universe? I don't know. But it's an interesting question, isn't it? Just given the vastness of the universe. It seems like a pretty likely possibility is that there is life elsewhere in the universe, but that so far away we'll never see it. So in other words, aliens showing up on our doorstep, probably not terribly likely. And so yes, maybe there's life elsewhere in the universe, but that we'll never see it. On the other hand, that doesn't make for nearly as compelling a story, right? As if there is life in the universe, and we do encounter them. And so in Trevor the Time Traveler, I explored the possibility that there is life in our galaxy. And in fact, in Trevor the Time Traveler, I made the assumption that there are around 3,000 life forms in the Milky Way galaxy. And in the Andromeda Galaxy, there are around 10,000 different types of life forms. Now, why 3,000? Well, if there are 300,000,
You're pointing at
no, I'm pointing at myself. Oh, good thing it's not a gun. I would have killed myself. So if there are 300 million stars and only 3,000 of them have life on them, that's still only 1 in 100 million. Did I do that right? Yeah, that's only 1 in 100 million have life on them. So I'm figuring, okay, let's imagine 1 in 100 million stars has life on a planet orbiting it. That still gives us 3,000 life forms in the Milky Way galaxy alone. So I figured, okay, I'll use that number. And then that would give us around 10,000 life forms in the Andromeda Galaxy. Now let me tell you some backstory. I don't want to spoil the story because most of you probably haven't read the story yet. But here's something that's true. The Andromeda Galaxy is on a collision course with us. And in fact, they can do very careful measurements of the Andromeda Galaxy and figure out which way it's moving. And it's heading straight for us. And in fact, the Andromeda Galaxy is going to collide with the Milky Way Galaxy in about 4 billion years. I know, I'm really worried too. Yes?
Sort of like an asteroid galaxy that's about to hit like our galaxy and that make one too big.
Yeah, so I mean, the question you're asking, I think, and I think there's two questions you're asking. One is, should we invest in the stock market given that the Andromeda Galaxy is heading straight for us? Right? And it's in 4 billion years, so go ahead. But the other question is, what's going to happen in 4 billion years when the Andromeda Galaxy hits our galaxy? The answer, by the way, is nothing particularly bad. It turns out that galaxies are mostly empty space. Right? I mean, if you look out in our galaxy, right, it's almost all empty space, right? So you've got to go 4 light years before you can get to the next closest star. So when two galaxies collide, which it's happened before, it's going to happen again, it's not a big deal. They come together like a flock of birds. The gravity holds it together. But no two stars actually hit each other. Yes?
Well, wasn't there a series that there were black holes in the center, so wouldn't the black hole in the center suck up everything?
Well, it's a concern, right? I mean, you're right. There are very massive black holes at the center of all major galaxies, it's thought. In fact, in the Milky Way galaxy, there's a black hole that's 4 million times the mass of the sun. And they've taken pretty good pictures of stars going around it, and they can figure out that the black hole at the center of the Milky Way galaxy is 4 million times the mass of the sun. There's almost certainly, I don't know how well it's been measured with Andromeda. I suspect it has been. I don't know how massive it is, but probably millions of times the mass of the sun would be the mass of the black hole at the center of the Andromeda Galaxy. And it just turns out, though, that it's hard to fall straight into it. It's sort of like if you want to fall into a black hole, it's just not as easy as it sounds. It's sort of like if you were to take your dog's watering bowl outside and you got a water hose and you're trying to fill it up, but you have the water hose going too fast and the water just goes in there and splashes out, right? It's kind of a similar thing about falling into a black hole. You got to be a pretty good marksman. You got to fall straight into it. Because if you don't fall straight into it, what happens is you get whipped around it and it gets sent back out. And so actually, you would think, for example, why doesn't the Earth fall into the sun, for example? Can anyone tell me why the Earth doesn't fall into the sun? Yes?
Because it has the same effect as the black holes.
Yeah, I mean, well, the Earth is, by the way, the Earth would fall into the sun if you stopped it, right? Then it would fall straight into the sun. But because it's moving around the sun like this, it has momentum. And so it's sort of falling into the sun all the time. And in fact, let me draw a picture to kind of illustrate this point. I'll turn a light on here. This is one of my favorite. This is, by the way, I'm about to show you a great idea. This idea is, roughly speaking, due to Sir Isaac Newton, who realized that the motion of the planets is closely related to the motion of rocks that you might throw on the planet Earth. So if this is the Earth, for example, and now suppose you go to the top of a tall mountain, and on the top of the tall mountain you put a cannon, and you fire a cannonball. The cannonball will come out and hit the Earth right there, right? But now suppose that you fire the cannon even harder. It'll go further, right, if you fire it faster. And now suppose you fire the cannon even faster. Then it's going to go even further before it hits the ground. It so happens, now suppose you get the most powerful cannon ever devised, right? And it's just so powerful, you fire it, and it just goes off into deep space. Well, there's a halfway point where you don't fire it, you fire it faster, so fast it doesn't ever hit the Earth. On the other hand, not so fast that it leaves the Earth's gravity. You can fire it just right, and then what happens is it goes in orbit around the Earth. And so if you want to understand what the moon is like a rock like any other. It's a very big rock, of course. But in fact, it is a rock that's falling towards the Earth. It's just that it keeps missing it, right? So here's the Earth. Here's the moon. The moon is trying to fall to the Earth, but because it's already moving this way, it's trying to fall to the Earth. It's always accelerating that way, but it keeps on falling to the Earth, but never quite makes it because it's moving so fast tangential to the Earth. So actually falling into the black hole is the same thing. It's not as easy as it sounds. You'd have to be headed straight for it. Yes?
But if it was like, if it shoots the planet like back, wouldn't the planet just hit something else?
Well, the way you answer these questions is you've got to solve complicated equations. And it just turns out, Newton did this, is that the motions of the planets around the sun and the motions of the moons around planets is exactly the same equations that would describe if you take a rock and throw it into the air, or take a cannonball and fire it out of a cannon. These are described by exactly the same laws of motion. And that's quite surprising if you think about it, isn't it? It's not really obvious. Maybe today we take it a little bit for granted, but it was non-trivial in the day of Newton. So we've got the other questions. I'll take some questions. Anyone have a question they want to ask? Question, yes? Yes?
How come it doesn't happen to radio waves? How come the radio wave just goes like that? How come it doesn't like keep traveling around and around and around? Because like...
That's a great question. So the question is, why do radio waves not obey gravity? And actually, radio waves do obey gravity, it turns out. And this is due to Einstein. So that's a great question you just asked. And what radio waves are just a different frequency of light. And what's been measured is that the gravity of the sun actually does bend light. In fact, if you look at starlight that goes right next to the sun, it does get bent by the sun. The only thing about it is if you're going very fast, then gravity doesn't affect you very much. And so since radio waves go so fast, like on the planet Earth, they get shot out into outer space. And mostly the gravity of the Earth isn't able to slow them down because they're going so fast. So that's the difference. Yes, another question?
Since black holes' gravity is so strong that even light gets bent by it, so why would the planet just get thrown out?
Why wouldn't the planet what?
Why wouldn't the gravity be so strong that it would just suck it in?
You're talking about a planet going around a black hole?
Yeah, wouldn't it just get sucked in?
Well, you would think so, but it's, when you solve the equations, it turns out that you can still get orbits going around black holes, just like you can get orbits going around the sun. So I know it's counterintuitive, like why doesn't the Earth fall into the sun? Why don't all the planets fall into the sun, for that matter? And actually, guess what? Most of the mass of the solar system did fall into the sun. In fact, one thing I can describe for you very quickly is how the solar system was created. Right? There's something it's really an amazing story here. And in fact, it's not just how the solar system was created, it's how galaxies were created. And in fact, it's not just how galaxies were created, it's actually, to some extent, part of the story is how the universe was created. Unfortunately, I don't know the answer to all of this. When we talk about where did the universe come from, nobody really knows. Everyone wants to know. Nobody really knows. So there's a lot of possibilities on this. If you look out at the universe today, you'll see that the universe is expanding. And so what does that mean? Well, it means, roughly speaking, the universe looks like a balloon that's being blown up. So let me turn the lights on again. So if you take a balloon and put a bunch of dots on it, each of these dots represents a galaxy. Now blow up the balloon and make the balloon even bigger. Then what you'll see is that these dots got further away, didn't they? Just by the fact that you blew up the balloon makes everything get further away from everything else. And that's actually a very good analogy about what's happening in the universe right now, is that the universe is expanding. Everything is getting further away from everything else. And initially, and so when you see that we're on a balloon, the balloon is expanding, well then what does that mean? It must mean that the balloon was even smaller in the past. So if the balloon's getting bigger now, it must mean that if you go into the past, it was getting smaller. And in fact, they can even see the universe in the past. Because remember, light can only go so fast. So when you look at something that is 5 billion light years away, that means it took the light to get 5 billion years to get to you. So every time you look at something 5 billion light years away, you're actually looking into the past by 5 billion years. And so people spend their lives, astronomers spend their lives looking into the past. And what they see is the universe is getting bigger. Now what that means is that if you keep playing it back, maybe the universe started out as maybe infinitely small or something. And that's called the Big Bang Theory. And there's some things about the Big Bang Theory that are almost certainly true. But there's some things about the Big Bang Theory we just simply don't know. Question, yes?
One of the things that you said before,
Yep.
does it mean that we're seeing stars as they were like a billion years ago?
We are, yeah. We're seeing, when you look through a telescope and you see a star that's a billion light years away, you're seeing a star as it looked a billion years ago. So you can look back into time. So being an astronomer is a really cool job. Another question, yes?
The light can get from a black hole. Is there light in a black hole?
So what's interesting about black holes, which by the way is predicted by Einstein's theory of general relativity, and also black holes have been essentially seen, sort of, right? What does it mean when you see a black hole? Well, the problem with black holes is you can't really see them. First of all, they're black, right? On a black background, so that's kind of hard, right? The second thing is that once anything, including light, goes into a black hole, it can't get out. So on the other hand, if you were to go inside a black hole, everything would seem reasonably normal. You could still be able to look into a mirror and see yourself. There's light inside of a black hole. It's just that that light can't get out of the black hole once it gets in. The only other thing that would be kind of weird is as you approach the singularity of the black hole, you'd be stretched and turned into spaghetti. And that would probably be a little bit uncomfortable. And you would be what's called spaghettified, and you would take something that's a normal shape and you'd be made very long and very skinny. So essentially then the current theory is that you would fall off the edge of the universe essentially. And if you don't think that sounds like a very satisfying theory, then that makes all of us. Because understanding what happens inside of a black hole is an open problem. No one really knows because no one's ever been there. And the theories get very extreme, and so it's hard to say for sure what the truth is. Yes?
So with the cosmic microwave background radiation, is there one direction where it comes from, or is it just from everywhere?
Great question. So that question actually gets me back into the Big Bang. And it turns out the universe is in terms of people, what we know today is roughly as follows.
Can you turn the light off? It's making it hard to see.
Okay. Okay. So what seems to have happened after the Big Bang is that almost all of the universe was light. Okay, so I'm giving you the modern physics interpretation of how the universe began. There was a Big Bang, and then for a long time, most of the mass of the universe was light. And that was true for around 50,000 years. Now, I know it sounds weird. How can light have mass? But it turns out there was just so much energy in the Big Bang in the form of light that it actually had mass, and most of the mass of the universe was light for the first 50,000 years or so. And then somewhere around 200,000 years after the Big Bang, and by the way, it was so energetic, the temperature was even hotter than inside the sun. Okay, so it was a very, very hot environment, right? And so you wouldn't want to be back there. No way we could exist back in that time, even though Trevor does go back to the beginning and explore the beginning of time. But he has a very special time machine that makes that possible. So after, and in fact, it was so hot, there was regular matter. But you all know that regular matter is made out of molecules. And those molecules are made out of atoms. And those atoms are made out of protons, neutrons, and electrons. And it was so hot that there weren't any molecules. And in fact, the atoms got ionized, and the protons and neutrons were split away from the electrons. And so it was actually a plasma universe, just like inside the sun. And you had electrons and protons separated and ionized. And so light was bouncing around everywhere, but it couldn't go long distances. Somewhere around 200,000 years after the beginning of the universe, after the Big Bang, the protons, neutrons, and electrons came together. It's called reunification, recombination. And so when the electrons and protons and neutrons combined, then all of a sudden you got hydrogen gas everywhere, mostly. and it was no longer a charged universe, and the amount of light was going down. It wasn't quite so bright and quite so hot. And what happened at that point is, since it was no longer a charged universe, light all of a sudden could travel long distances. And so you went from this big fireball of stuff to all of a sudden matter started clumping into galaxies, and light started traveling long distances. And so that light, you're asking me about what is the cosmic microwave background radiation that you've heard so much about. That's the afterglow of the Big Bang. That's the afterglow of when the universe was mostly light. And that's that light finally going long distances. So after that, matter started clumping into galaxies. And dark matter, which is a very mysterious thing, probably started clumping into galaxies even before that. And there's a very interesting phenomenon which caused galaxies to be disk-like. Do y'all know how you have a lot of spiral galaxies like the one on the cover? Let's look at some more pictures, in fact. There's another disk galaxy. There's the Andromeda galaxy, even bigger. That's the sun. Let's see. I guess that's all the pictures of galaxies I have. So first of all, you know, the solar system is like a disk, and the Milky Way galaxy and the Andromeda galaxy are like disks. And so what happened is that as matter was coming together, it just started swirling around. And why did it start swirling around? Well, have you ever seen a figure skater and how she can spin really fast? And the way she spins really fast is she brings her hands in. She starts spinning, right? I'm not going to do that, okay? But she starts spinning, and then she brings her hands in to spin really fast. Well, that's what happened when matter came together in galaxies. It was already just sort of spinning a little bit by random chance. And then as it started having friction and coming together, it started spinning faster and faster and faster. And that's the phenomenon that sort of made galaxies kind of like disks. And that same phenomenon, by the way, is what made the solar system a disk. Most of the mass of the solar system, by the way, did fall into the sun. To address your question, you know, why doesn't matter just fall into the sun or fall into a black hole at the center? Most of the mass of the solar system did fall into the sun. That's why the sun is practically all the mass of our solar system. Almost all the mass is inside the sun already. But some of it was lucky, and some of the mass of the solar system didn't fall into the sun and got into orbits around the sun, and then later it clumped to form planets. I have a question in the back there. Yes?
How big can black holes get?
Well, that's a very, what would you say, current question that you asked, because until a few weeks ago, the largest black holes that had ever been seen were on the order of 4 million times the mass of the sun, or 10 million times the mass of the sun, that order of magnitude. And recently they discovered at least they claim to have discovered a black hole that I think was, does anyone remember? Was it so many billion? Was it 5 billion or 10 billion? 5 or 10 billion times the mass of the sun. And so there's no limit. Theoretically, there's no limit as to how big a black hole can get. But still, black holes, as big as they are still not most of the mass of a galaxy. Most of the stuff in a galaxy is not inside the black hole at its center. Yes?
Well, so do black holes get larger? And how are they created?
That's a great question.
I think that it's because something happens to a star.
Mm-hmm.
So
it's first of all, it's a complicated question, and there's what is known by human beings today, and then there's what subset of that I know, okay? So let me tell you what I know about it. It's known that there are certain types of stars that, that are so massive that they will become black holes. Or put another way, if you look at stars out there, let me get my story straight. If you look at stars out there, I'm a mathematician, by the way, who's gotten very interested in astrophysics. And I've become decently knowledgeable, but I'm still not a professional astrophysicist. This is kind of like my hobby, part-time kind of thing. But by the way, I hope everyone realizes you never let anyone define you, okay? You can always learn more and more. But what the conspicuous fact about stars is that stars are only so massive. So like our sun, for example, is an average-sized star. And there are stars that are 2 or 3 times bigger than our sun, but there aren't any stars that are 100 times bigger than our sun. And that's weird. Like, well, why not? Why can't gas and dust collapse and form a star that's 100 times the mass of our sun? And the answer is, well, or the best guess people have is that whenever that happens, you get a black hole. So if you look at stars only get so massive, and after that, they just don't exist, or we can't see them. And the reason is thought is that, well, it's because they collapse into a black hole. And if you go through the physics of it all, of how that collapse would happen, it turns out the maximum mass for stars is well predicted by the theory. So this matches out very well. Yes?
Like, what exactly is dark matter?
That is a great question. I am obsessed by that question. What is dark matter is the question. My research is right now in part focused on trying to understand what dark matter is. And there's something really, I'm about to tell you something, by the way. Let me tell you what dark matter is. And if this doesn't blow your mind, then I guess you're not listening or something. I don't know. All right? Because I don't know how this couldn't blow anyone's mind. If you look at this picture of Andromeda, what shape would you say it is? Like a frisbee, right? It's like a disc, kind of like a frisbee. Let's call it a frisbee. You ready? It turns out that most of the mass of that galaxy is invisible. And not only that, it's called dark matter. And not only is it invisible, it's not even shaped like a frisbee. It's shaped like a basketball. So the shape of that galaxy, by the light that you can see, by the light that it emits, the shape of that galaxy is a frisbee. But the shape of that galaxy, by its mass distribution, is a basketball. They have the same center. You can't see it, but just visualize a basketball there, the size of that galaxy. All right? Now, how do they know it's there? They know it's there by its gravity. So for example, let's do a thought experiment. Imagine the sun was invisible. Well, that would be bad, wouldn't it be? Because then it would be very dark here very quickly, right? OK, well, let's suppose we had electricity to keep the lights on, something, I don't know, right? OK, but imagine the sun just disappeared. It became invisible. It's still there, but it's invisible. How would we know what the mass of the sun is? Can anyone tell me how you could figure out what the mass of the sun is, even if it were invisible? Yes?
You could feel it, sense it.
We can feel it, in fact, because you can look at the planets, right? The planets go around the sun, and based on the motions of the planets, in fact, you can estimate the mass of the sun. And in fact, guess what? That's how we did it anyway. The only reason we know what the mass of the sun is by looking at the motions of the planets, right? It's not like someone went over to the sun and weighed it, right? You can't do that, right? So you look at the orbits of the planets. That tells you how massive the sun is. And the fact that you can see the sun is irrelevant, right? You don't actually need to see the sun to figure out what its mass is. Same thing with dark matter. By looking at the motions of stars in galaxies, it just turns out that they're going faster than they should. And the fact that they're going so fast tells you there's more mass there that you can't see. And in fact, most of the mass of a galaxy is invisible. And we got to call it something so they can figure out, I don't know, what about dark matter? I said, what do you think? I don't know. OK, fine, dark matter. Why do they call it dark? Because you can't see it. They could have just easily called it invisible matter or whatever they want. But no one really knows what dark matter is, except for me. No, I'm just joking. No, I would like to know. I have a theory, but I'm still working on that. Yes?
Is there dark matter in this room?
Yes, there is dark matter in this room. Just not very much. So the scale of the universe is so large, it's hard to get these orders of magnitude straight. But most of the massive galaxies is dark matter. But it's roughly evenly spread over the galaxy. And so there's dark matter in this room. There's dark matter between Earth and Mars. There's dark matter between the stars. But because it's spread over the entire galaxy, whereas regular matter is concentrated on the planet Earth, most of the mass of the Earth is regular matter. That's right. We cannot detect it gravitationally on the planet Earth. Now, there is a very small amount of dark matter passing through the Earth. And here's something I find exciting. And this is, by the way, this is roughly speaking science fact I'm about to tell you. But everyone's trying to detect dark matter. If you could detect dark matter in the laboratory on Earth, let me tell you how exciting that would be. If you all heard of solar cells? Have you ever seen like a solar panel, right? And then sunlight hits it and you turn it into energy? Imagine you could do the same thing with dark matter. Imagine if you had a panel, but it wouldn't be a solar cell, it'd be a dark matter cell. And imagine that all the dark matter from outer space that hit it got turned into electricity. It turns out that that dark matter panel would produce 100 times as much energy as a solar panel, and it would work at nighttime as well. That would change the world, wouldn't it? And that might conceivably be possible. If there was a way of converting all the dark matter that hits a panel into electricity, you would have a solar cell that works 24 hours a day. That would be, so I would say dark matter is worth understanding. Yes?
So if dark matter is in a halo around our galaxy, why is it just invisible matter is in a disk and not in a halo as well?
Okay, so the question is, why is dark matter like a basketball, whereas regular matter is like a frisbee? Well, there's two things. First of all, some galaxies are like a basketball. So about half of them are like a frisbee. They're called spiral galaxies. The other half never actually collapse into a disk, and they're like basketballs also. And they're called elliptical galaxies. The reason regular matter collapses into a disk is because of that figure skater effect. And she comes in, the reason she brings her arms in is because of friction. The friction of all the matter rubbing up against itself, gas and dust, causes it to come in, and then it forms a spiral galaxy. The problem with dark matter is no friction. And so there's no reason for it to collapse. So there's no reason to get the pancake type shape. Great question. So, question, yes?
If the galaxy was expanding and the expansion was getting faster and faster, why would two galaxies start to collide with each other if they're supposed to be getting farther?
Great question. Okay, so the universe is expanding. On average, galaxies are getting further and further apart, but that's just on average. It turns out that galaxies that are close to each other have some randomness to their motion because of all kinds of effects that have happened in their past. And so galaxies collide all the time, it so happens. And in fact, the Milky Way galaxy is probably the result of many smaller galaxies coming together already. And so galaxies colliding happens from time to time. Let me end on one other thing. I just want to blow your mind one more time, okay? Again, this is, I find this amazing. The sun. By the way, that's a picture of Saturn. That's a picture. That's not, let me just tell you what that is. We sent a probe into outer space. It spent years getting to Saturn. Then it passed behind Saturn and got in Saturn's shadow. The sun is on the other side of Saturn. Then they went back and took a picture. And you can't tell, but there's a little dot over there on the right, and that's the Earth. All right? So that is an amazing picture. It just looks so surreal to me. On this projector, it doesn't show up. You can find this on the website later. That's an amazing picture. By the way, that's a moon of Mars. Doesn't that just look ridiculously alien? Like that's one of the moons of Mars. And then that's the crater, which is this huge object. That's the Earth and the moon taken from Mars. We have probes over in Mars, and they looked back and they took a picture of the moon going around the Earth. That's from Apollo 11 photo of, that's when we went to the moon. They took a picture of the Earth rising over the moon. That's just an all-time classic, of course. And that's a picture of the Earth, which, by the way, they spent billions of dollars making this picture of the Earth. That's not actually a picture of the Earth. They actually had satellite go around the Earth, and they took like hundreds of photographs, and then they projected it onto a globe, and that was a composite image. So someone spent like years working on that probably. All right? It's a pretty cool picture, so I put it on the back of my book for free. That's a picture of the moon from the International Space Station, which is pretty cool. That's the atmosphere there. That's the troposphere in orange. You can actually see the layers of the atmosphere there. And that's a recent Martian impact. So on Mars, they took a picture of that spot, and there wasn't anything there. And then 2 years later, they took a picture, and there was that there. All right, so somewhere between 2010 and 2012, something hit Mars and left that crater impact, which is pretty cool. But let me go back to the sun here, because there's something really amazing about our sun. And I'll end on this idea. I think my time is up. What's amazing about the sun is that, first of all, it gives us all of the energy on the Earth. It's almost all the energy, except for a little geothermal energy. Right? So life could not exist without the sun. So we have to be really thankful for the sun. But it's more than that. It's not just that that stars light up our world, or this star in particular. There's something much more fundamental about stars. And that is based on the best thinking that scientists and astronomers and astrophysicists have today. Right after the Big Bang, almost all the regular matter in the universe, like what's in the periodic table of elements, almost all of it was hydrogen. Practically all of it was hydrogen. There wasn't hardly any of the other elements, like oxygen that we breathe or carbon that makes up carbon-based life forms. This did not exist. There wasn't any of it in the universe after the Big Bang. So how did we come into being? Well, galaxies formed, and inside galaxies, stars formed, and the hydrogen collapsed into stars like that. And what powers a star is called fusion. The hydrogen molecules at the very center of the star are getting pushed together, and two hydrogens form a helium. And then a helium can get pushed together with a hydrogen and maybe form a lithium. And very complicated nuclear reactions that only happen inside stars are happening inside our sun and other stars. And what happens with some stars is when they get big enough, they explode. And so all these other elements like carbon and oxygen that make up our world were created inside stars and did not exist except for stars. And then some of them exploded. And then all these elements went into outer space, and some of them collapsed into new stars, and the whole process repeated, and some of them exploded, and then created even more elements, and they collapsed into stars. And even more elements were created, and those stars exploded, until finally some of that gas and dust with these heavier elements like carbon and oxygen came over to our part of the universe and started swirling around. And most of it collapsed into the sun, but some of it didn't and was orbiting around the sun. And some of it was heavier elements like iron and formed rocky planets like the Earth. And some of them got water and other compositions possibly from comets, who knows, right? And so the deep thought is that all of the matter in this room, except for hydrogen, all the matter in this room, except for the hydrogen, was once inside, was in fact created inside stars. We are all made out of stardust. We were all made out of matter that was once at the center of stars. That blows my mind. I don't know about you guys. All right, one last question, and then we'll call it a day. Yes? Go ahead. Say it again?
Could there be 1 billion suns in another galaxy?
Absolutely. In fact, each galaxy has 100 billion stars, and there are 100 billion galaxies. So the universe is just amazingly large. Great question. Any other questions? Maybe one last one? Okay.
So, at first, why don't we, when we take a shower, how come we don't go down and drink?
That's a great question. But how about we answer that afterwards? You can come up and we'll talk about it. And what I'm going to do is now is we have there are books for sale outside. I make $1 each time you buy a book, so it's really important that, no, I'm joking. I hope you enjoyed the book. There's for sale outside. It's also available on Amazon.com. And I will stay here as long as there's anyone here to talk to. And so you can, I'd be happy to sign copies of the book and also answer more questions if you just want to come up to the front. So thank you all for coming out. It's been a pleasure.
Well, so as we just said, we're going to be around for a little bit. Don't worry about it. The bookstore, however, told me they're going to leave around 9. So that's all you need to know. And I want you to join me in thanking Hubert again for sharing with such a passion. I think that it makes me excited about all these things. I don't know about you. Any of young kids here excited a little bit? And so you might not sleep tonight, but that's okay. Thank you.
Thank you.